So in this lecture, we're going to look at the kinetic energy to see if that equation also has to be modified. So just our Lorentz transformations before. The only difference now we have is we have this new definition of momentum. Just remember, this is the square root of 1 minus u squared over c squared, not the v squared. And we still want to keep this Newton's second law. We at least want to keep this definition of force, which is the force is the change in momentum with respect to time. But here I'm going to talk about kinetic energy. Again, on that first homework assignment, we said if the kinetic energy is conserved in Franck's frame, then when we transformed it using the Galilean transformations, it was conserved in Franck's frame too, and vice versa. But we want to see, does the definition have to change like we did with momentum? Well, how did we define kinetic energy? Well, the way we define kinetic energy is the total work. The total work on a system, which we defined as the integral. You're going to go from, say, A to B. You're going to go from A to B of F dotted with ds. That was the definition of the total work moving an object where that's the total force dot ds. And that ended up being the change in kinetic energy, which is the final kinetic minus the initial kinetic. Okay, well, let's just say the object, whatever we're looking at, starts from rest. So that way, we can just get rid of that, and we'll just say that's the kinetic energy if you start from rest. Okay, and let's also, just to make life a little simpler, why don't we make F and ds in the same direction? So that would mean when we take the dot product, the cosine of 0 is 1. And so this final kinetic energy, or just K, is just the integral from the beginning spot to the end spot, A to B. Well, we're going to A to B of F ds. Okay. Well, what did we say F was? F is the change in momentum with respect to time. So we're going to change that to A to B of, in place of F, I'm going to say it's the change in momentum with respect to time times ds. Well, since you're moving at a speed u at any time, we know u is ds dt. That's the definition of velocity, is the distance over the time. So ds is just u dt. Okay, so I'm going to replace ds with u dt. So this is integral from A to B of dp dt. Well, yeah, actually, why don't we replace this with d dt of, we'll plug in what momentum was right here. Momentum was mu all over the square root of 1 minus u squared over c squared. And then we have ds, which is u dt. Okay, well, we can cancel the two dt's, which that cancels with that. And now, how do we handle, well, let's write it down first. So we get k is equal to the integral from A to B. Actually, what's changing is really the speed in here. It's changing. So we're going to go from, well, we're going to go from 0 speed to some final u. Well, if we're going to go to some final u, then I don't like u's inside the integrand right here. So what we'll do is I'll just make them u primes. They're not Marys, they're just a dummy variable, mu prime all over the square root of 1 minus u prime squared over c squared times u. I'll put the u out here, put the u right there. So that is what the kinetic energy is going to be. Now, how do we integrate this thing? Well, it looks like the easiest way to integrate this is by parts. Our first integral right here in the whole course so far, our first little bit of calculus. Well, if we're going to do parts right here, why don't we let u equal u? That's nice. And dv, we'll just let it be d all this. D mu prime all over the square root 1 minus u prime squared over c squared. And now we need a du over here. Du equals du. And v is just this without the d. So v is just mu prime all over the square root 1 minus u prime squared over c squared. Okay, so now we can apply the parts to this. So k, what do? You do u times v, so it's this times this. So this is, this would have been a prime, and so this was all prime. So you'd have u times v, so that's mu prime squared, divided by the square root of 1 minus u prime squared over c squared, evaluated from 0 to u, minus the integral of v du. This du. So if we so it would just be minus the integral from 0 to u of this du, mu prime, all over the square root of 1 minus u prime squared over c squared. Du prime. So we just integrated it by parts. Now we can plug in these limits right here. When you plug in 0, you get 0. So all I have to do is plug in the top one, which means all my u primes just go to u's, back to u's. So we get k is equal to m u squared all over the square root of 1 minus u squared over c squared. And then we still have to integrate this thing over here. Well, let me see, how are we going to integrate that right there? Well, I figure we might want to do is, how about since I know the derivative of u squared is like a 2u, and we have one up in the top, why don't we try a u, well, I don't want a u substitution, I've got enough u's. How about an r substitution? Why don't we let r equal to this, everything inside the square root, which is 1 minus u prime squared over c squared. Okay, and now if I take the derivative of this, we get dr equals 0. You get minus 2u prime du prime all over c squared. All over c squared. Or I think I need see I have a u prime du prime. I'm going to solve for u prime du prime out of this. So we'll bring over the c squared and we'll bring down the minus 2. So we got u prime du prime is equal to, it's going to be a minus. We're bringing the minus over. We're bringing the c squared over. We're bringing the dr over. And we're bringing the 2 down below. Okay, so this now becomes minus the integral. Now my limits are going to change. I'm not going to put, I'm not going to change the limits right now. We'll go back later and put back it in for u. So I'm just going to keep it still from 0 to u. We won't plug them in yet. We get m. Then we get u du, which is right here, which is a minus, which makes that a plus, c squared dr over 2 divided by the square root of r. divided by the square root of r, divided by, well, square root of r is just r to the 1/2 power. Okay. So that I can integrate right there. Okay, so this becomes, this k becomes mu squared all over the square root of 1 minus u squared over c squared. I can pull out the mc squared over 2 plus mc squared over 2. And all we have is the integral of 1 over r to the 1/2. Well, actually, let's just say it's r to the, bring it up, it's r to the minus 1/2 dr. Well, integral of r to the minus 1/2 is r to the 1/2 all over 1/2. So this would just be r to the 1/2 divided by 1/2. Well, the 2's drop out, so we get rid of the 2's. And we still have to evaluate it, but I'm going to plug back in what r is. So we got mu squared all over the square root 1 minus u squared all over c squared. And we got plus mc squared. Sounds familiar, mc squared. We get the square root of this, the square root of r, which is 1 minus u prime squared all over c squared. And we haven't evaluated this. We have to evaluate this from 0 to u. Okay, so now we still got this first term, mu squared all over the square root of 1 minus u squared over c squared. Then we get plus mc squared. Now when I plug in u, when I plug in u here, I get 1 minus the square root of 1 minus u squared over c squared. And then when I plug in 0, I get 1, because that's gone, so I get minus 1. Okay, we can simplify that further. So that means the kinetic energy now is equal to mu squared all over the square root of 1 minus u squared over c squared. Then we get mc squared times this plus mc squared times the square root 1 minus u squared over c squared minus mc squared. Okay, I think what I'm going to do between just these two, I'm going to get a common denominator. So I'm going to put down here a square root of 1 minus v squared over c squared, and I'm going to do the same thing with the top, which means it just gets rid of the square root. And so we don't have the square root. Okay, and now if I combine these two terms together, they got the common square root of 1 minus u squared over c squared. But now the numerator, I get an mu squared plus an mc squared minus an mu squared. Well, the mu squares drop out, and so I just get mc squared. That's all it is up there on the top. And then I also get minus that term on the end, minus mc squared. So there is my new definition of kinetic energy, and I got that from my new momentum. And since the new momentum is conserved, this will also be conserved within Frank's frame. Now, you notice our old equation was this. That was our old equation, 1/2 mv squared, 1/2 mu squared. If you go slow, does this term equal that term? It better. Well, remember, if you're going slow, this is a very small quantity right here, and so this this term without the mc squared, this 1 over the square root of 1 minus u squared over c squared, it looks something similar to 1 minus some little number, which we did before, to some power n. Remember, when epsilon, this little epsilon was very small, then this was like 1 plus n epsilon. So for us, that means this quantity right here will be 1 plus the n, which is 1/2, epsilon, which is u squared over c squared, u squared over c squared. Now, if I take this and replace it with 1 over this and replace it with that, you notice when you multiply this together, the mc squared will subtract off and you'll get no mc squared. And then when you multiply this times this, the c squared is gone and you get 1/2 mu squared. So this does equal 1/2 mu squared when you're going slow, but this is what it looks like when you're going fast. And if we were to plot it out, if you were to plot out, well, let's say this is kinetic and this is the speed, u right here. What you're going to get here is it's actually going to go something like this, and you're going to get an asymptote, horizontal asymptote, because we're plotting it out by k along here. So even it takes an infinite amount of energy, and all you can do is make the speed approach c. So at a particle accelerator, when they keep pumping in more and more energy into the particle, the speed is just barely going faster right here because they're way up near this asymptote. Now, you'll notice that the kinetic energy, it's a difference between two terms. This looks like the energy you have, since it has a u in it, this must be the energy you have due to your speed, or this is just the total energy you have, minus due to your motion, and then you're subtracting off this, which has no motion in there, 0 right there. So we can assume that when you have no motion, right here, your kinetic energy, your energy, this is just not kinetic, this is just your energy due to motion minus the energy when you're not moving. Your energy due to not moving is just mc squared, and that's where they get this equals mc squared from. It's just the energy you normally have, right, when you're not moving. But now, once you move, you also pick up kinetic energy, and the kinetic energy is this whole thing right here. So if you wanted to figure out, if you take the kinetic and you add it to your mc squared, kinetic plus mc squared, that must be your total energy. Because we'll see that there is no such thing as potential energy now. Remember in 4a and 4b and so on, you had something called potential energy. Here we have no potential anymore, it's gone. All we have is kinetic energy and mass energy. And so the total energy is just the sum of these two. That's your total energy right there. And you can see, if I just bring this over to this side, this term must be the total energy right here. So this is the total energy minus your energy due to your mass is due to kinetic. That's what you're saying there. So the total energy just ended up being mc squared all over the square root of 1 minus u squared over c squared. So there's your total energy. There's your kinetic energy. Well, you might say, well, when we had potential energy before, where does when I throw up a ball, throw it up in the air, where did all that kinetic energy go? Because I lost kinetic energy. If energy is conserved, it had to go someplace. Well, where did it go? It went into, if you lose this, it has to go into this. So the mass of whatever it is gets a little bit bigger when it got up here, And then when it came back down, it went back again, right here. So, or what happens if we have a collision where you stick together? You notice in classical mechanics, we called that a inelastic collision. We said that if it sticks, let's just say they stick right there, we said the kinetic energy before is not the same as the kinetic energy afterwards. That's why we called it inelastic. That's because the energy went into things we couldn't take into account, namely the noise, the vibration, and so on. But now, where does the kinetic energy go? It goes into the mass. This mass, M1, plus this mass, M2. This isn't the sum of the two masses. This is bigger than the sum of the two masses. All that kinetic energy went into mass. So mass is going to be, mc squared is a fluid right here. It can get bigger, it can get smaller right here. But all we have is kinetic and mass energy. That's the only thing we have, right? So, when do we use this formula for kinetic, and when do we use our old formula? And when I have mv squared? When do we, if we see a problem, how do we know which one we're going to use? Do we use relativity or not? I mean, this one is always the most accurate, but it might not be worth it because it might be 8 decimal places out or something. So usually the thing is if the particle you're looking at, particles have a rest mass, mc squared. If the kinetic energy is, let's say, the kinetic is more than 1/100th of that rest mass, then we'll use this. If you're less than 1/100th of the mc squared, if it's greater, we'll use relativity. If it's less, we won't use relativity. It won't be worth it to use it right here. That'll be our criteria right there. Now we might say, what are the units for energy? You know, in 4A classical mechanics, our units of energy, we had the joule, which was a Newton meter. So if you had an object here and we pushed on it with 1 Newton for 1 meter, that's how much work you put into it, and that's when if that's the only force, then all of it went into kinetic energy right there. And so that was our definition of the joule of energy. But here we don't want to use joules. The joule is way too much energy when you're talking about little atoms and stuff. So we use something called an EV. 1 EV is like 1.6 times 10 to the minus 19 joules. I'd say, where did they get the EV from? Well, from 4B, if I have 2 parallel plates and I put them at a voltage, let's say there's a voltage between these two, right there. And let's just say this is the plus, well, let's say this is the minus plate. And this is the plus plate. If we have an electron right there, he doesn't want to hang out. If I put him right there, what's he going to do? He's going to zip across over to this side. So what's pushing him? The electric field's pushing rather than, say, my hand is pushing it right here. And so we said the force is just, what is that, Q? It's just it's the Q, but the charge of an electron is just E times the electric field, and the distance is D. So you could say the force, so you could say the work is the force times the distance, so it'd just be the work is the force times the, which is E times D. But if we wanted to turn our electric field, if you remember, electric field is the voltage divided by D for a parallel plate. So this is E voltage. It's voltage divided by D times D. The 2 D's drop out and you get EVs. So 1 EV is just the amount the electron will, how much energy he acquires in going through 2 plates of 1 volt. But it's, all we need to remember, it's just a very small amount of energy. Now, So we've got these units called EVs. If you wanted, we can now put a prefix in front, meaning kiloeV, KeV. So that would be thousands of EV. Or if we put MeV, these would be in 10 to the 6 millions of EV. Or GeV, which is billions, 10 to the 9th EVs. Or TeV, which is trillions of EV, and then they keep going on. Now, if you go to the Large Hadron Collider, they get protons up to, get the proton up to about 14 TeV. So that's how much kinetic energy they put into it. Now, light has energy. Usually, if you're talking about just regular red light and blue light, all the light that we can see, they're on this scale right here. They're in the EVs. That's just visible part of the spectrum, visible. If you wanted to talk about the ultraviolet part of the spectrum, that's probably in the hundreds. The hundreds of EV is the UV part of the spectrum. And KeV is in the X-ray, usually the X-ray part of the spectrum, and the rest of these are in the gamma ray part of the spectrum, gamma ray. Gamma ray. Now, the particles, when particle, like an electron, if he's just at rest, he has an energy, E, which is mc squared. He doesn't have any kinetics, so the only thing left is that. His mass right here, this energy comes out to be about 511,000 EV. That's how much his mc squared is. But whenever people talk about the mass of a particle, they leave out the c squared. They say, what's the mass of an electron? They'll just say it's 511,000 EV. We're not going to say 511,000 divided by c squared. No, that's already implicit. They're just going to say it's this. They're kind of interchanging mass and the energy here. We could have put this in KeV. It'd be 511 KeV. It's the same thing. Or we could have put it in MeV, 0.511 MeV. So those, all the particles will have a certain amount of EV. That's their mc squared. And so when we go through the particle zoo, each particle has its own unique mass. Right? You notice the particles all have energies way up here near the gamma ray part of the spectrum. So when nucleus decays, usually you get gamma rays out because that's kind of energy you're getting from these particles decaying. Okay, so we'll use EVs quite a bit for our energy, so next time the next couple of lectures we'll try to do a lot of problems where we can now solve stuff using energy and momentum. We don't want to use it using forces and using Newton's laws. We want to use it using energy because we know energy is conserved in Frank's. We know it's conserved in Mary's too. But we still haven't figured out our transformation equations for momentum. That doesn't mean that we're still going to have transformations for momentum and for energy. Okay, but we'll worry about that later. Okay.